The last video we talked about how to represent the states of a coin as a superposition of two eigenstates, either a heads or a tails, and we said that we're going to relate this eigenfunction or wave function of the coin to something analogous to what a vector would be on a two-dimensional plane. The only difference is that now, instead of having our x and y axis, we're going to have two axes that represent two different states. The horizontal axis represents the state of heads, and the vertical axis represents the state of tails. And we said that each eigenstate is in fact just a basis vector that points in each of these specific directions. And the scalar quantities that are attached to these two eigenstates, or these two basis vectors, are simply probability amplitudes. So the probability that it will either land on the heads or the tails. This is what these two scalar quantities are in this context. And we said that we can actually extract individual probabilities by doing something called the inner product, or simply the multiplication of a bra by a ket, and that would allow us to extract the probability of actually landing on a heads or a tails, depending on which one we multiply the coin's eigenfunction by. Now, I didn't talk about bras and kets in a lot of detail, so what I want to do in this video is continue talking about that in more detail and really discuss where this comes from. So essentially, Dirac, or Paul Dirac, who was one of the main contributors to quantum theory and quantum mechanics, there's this notation that is named after him, which is essentially the use of the representation of a vector by the use of these angle brackets and this straight line. So basically, what we call a ket would just be some sort of column vector that would have some finite or even infinite number of different scalar quantities, and basically each scalar quantity exists with respect to some eigenstate. So for example, this would be the probability amplitude of that function being in this first eigenstate. This would be the second probability amplitude corresponding to the probability of being in the second eigenstate, and so on and so forth. So basically we can represent this using the same notation here. So let's say probability 1 of the eigenstate 1 plus probability 2 of the eigenstate 2, and then we continue this to whatever number of elements we actually have defining that particular system phi. So the general idea is, well, how do we actually get an opposite operation out of this? Because let's say we wanted to multiply two quantities together. Let's say we wanted to multiply two kets like this, just for the sake of creating some operations with these quantities. So what do you think would happen here? We have two column vectors that are multiplying each other. This one has a number of elements, so we're going to assume that they both have the same number of elements, of course. What do you think would happen when you multiply two column vectors? What do you get out of this? Well, if you know elementary linear algebra, you will actually know that this operation is prohibited because you essentially have two matrices that have mismatched dimensions. So if we trace out the number of elements in this array or in this vector, we have n number of rows times one column. How about this one? We have n rows times one column. And the laws of linear algebra tells you that you cannot actually multiply two arrays together if the number of columns in the first one is not equal to the number of rows in the second one. So this operation is prohibited. Now, we can represent the sort of the kind of like the anti-eigen function, or just the complex conjugate of the function as a bra. So basically this would be just a row vector because we're going to take the transpose of this. So we're going to write the elements now as a row vector. But now we're going to take the complex conjugate. So basically we're going to have the complex conjugate of each of these. So this is just going to be the row vector of the complex conjugate of all those probability amplitudes. And you might be thinking, well, if we're talking about probability, how is it possible that a probability amplitude would actually be complex? Remember, probability amplitude is not the same as a probability. A probability amplitude is just a complex number that exists in this space, which is actually called the Hilbert space, denoted by this letter H. And the probability amplitude is a probability quantity that is associated with an eigenstate, but it is not a probability that we can measure. In order to measure a probability, you need to apply some operation, and the common operation that we use is called the inner product. So the inner product between two eigenfunctions or two wave functions is essentially defined as the sum of all the elements, so whatever n number of elements we have, from k equals to 1 of the elements phi k and psi k. But remember, because we're dealing with a bra here, this would actually be the complex conjugate of that element. So we would get something like phi 1 complex conjugate times psi 1 plus phi 2 complex conjugate psi 2, and so on and so on. And you might be thinking, well, that still does not answer the question. What happens when we have a complex probability amplitude? Do we get a complex probability out of it? That would make no physical sense, but that's not really what happens, because I can show you that if we were to take the probabilities of all these quantities, so let's take the inner product of phi with itself. Now this would just be the sum to n of all the elements of phi, so we would have the complex conjugate times this quantity here. So this is just going to be phi 1 complex conjugate times phi 1 plus phi 2 complex conjugate phi 2 plus so on and so on. Now obviously we're adding up all these probability amplitudes, so it makes sense that in adding all of them we should get 1, because if we are adding all the probabilities that exist for the system phi, we need to make sure that the probabilities all add to 1 if we want probability to be consistent with the laws of mathematics. Otherwise, we need to normalize our functions in order to yield the desired results. But we still have this complex quantity here, so it's a little bit uneasy, because if the probability amplitude is a complex number, then how on earth are we going to make sure that the probability adds up to 1, which is a real number? Well, here's how you do it. I'm going to take a generic number, generic complex number. I'm going to say z equals to 8 plus ib, where I squared equals minus 1. That's the definition I'm making here. The second thing I'm going to say is, let's say z asterisk is the complex conjugate of z, which means that we're going to take the opposite sign of the imaginary part. And now what happens when I multiply these two quantities together? Well, what happens here is very simple. We're going to grab it and we're going to multiply. It doesn't actually matter in which order we multiply this, but it is going to matter when it comes to this. I'll get back to that in a sec. First thing we do, we take the complex conjugate times that. So we're going to have a minus ib times a plus ib. Now we're going to expand this out. So we're going to have I squared. We're going to have minus I squared times b squared. And then we're going to have, the other two are going to cancel out. We're going to have aib minus aib, essentially. Now, what's I squared? We already said that's minus 1, so we have minus 1 times minus 1, that's plus a squared plus b squared. Alright, So we just proved that a complex conjugate of a number times the complex number itself always gives us a real quantity, because these two numbers are real numbers. Okay, but how do we associate this with anything remotely related to a probability amplitude? Well, the simple thing we do is we do the following. We know that the magnitude of a complex number is simply the square root of the square sum of its elements. So we have the real part, the imaginary part, but they're both real numbers. So that means that this relation here needs to hold. If we square both sides of this equation, we're actually obtaining this, which is essentially just the complex conjugate of z times z. So what this means is, by bringing it back here, we can actually redefine the inner product of an eigenfunction with itself, no matter whether it is actually complex or real. And we can say that we already proved this if we take a sum to some number n of elements, complex conjugate times the number itself is the same as the sum of the magnitude of the complex number. So we have the complex number here squared. And what happens with this? Well, you're going to have a sum of real numbers. Because even if the magnitude itself didn't convince you that this was a real number, you're squaring that, and basically you know that these have to be real numbers. So that's it. That's what we have defined. We have defined the inner product of an eigenfunction with itself to be the sum of the magnitude of the scalar quantities, or the probability amplitudes, squared. So that's all good. Now, the next thing that we need to pretty much define is a condition called orthonormality. So orthonormality says that two basis functions, or two eigenfunctions, however you want to call them. So let's say we have our heads here and we have our tails here. If the wave function is a valid wave function, then it will be decomposed as a sum of basis functions that are all orthonormal to each other. And what I mean by orthonormal, from a geometrical sense, what I mean is they're perpendicular to each other. So if we take a regular vector on the xy plane, we have two basis vectors. The first one is called I hat, and the second one is called j hat. And we know for a fact that if we represent each unit vector in terms of two coordinates, or in terms of two elements rather, on this 2D plane, then we know that each of these is only going to exist in one direction. For example, the unit vector I has only a magnitude along the x direction, but it has zero magnitude along the y direction. So in essence, these two vectors, these two basis vectors, are orthogonal. Another way we can prove this using vectors is by taking something called the dot product of two vectors. So if I take the dot product, this is essentially defined as the sum to n of all the elements equals 1 of ikjk. And look at what happens here. We have two elements only. So the first one is going to be 1 times 0, and the second one is going to be 0 times 1. So this is going to be equal to 0. And we can generalize this to any number of dimensions. And we say that two vectors, not necessarily unit vectors, but two vectors in general, are orthogonal or perpendicular to each other if their dot product is equal to 0. But hang on, isn't the dot product similar to what we just defined as the inner product? And in fact, you would be right, because the inner product of two functions, as we have done here, is in essence just the dot product of two vectors, because remember that we're talking about eigenfunctions as if they were vectors, and to some extent in this discrete version that we're defining here, they are vectors. So this is just going to be the dot product of those two vectors from k equals 1 to n. And this is how we represent that. But an even more powerful thing that we need to take into account here for when it comes to the inner product is that this actually extends to a whole lot of more cases. So it doesn't actually just hold for finite quantities like vectors, but it also holds for continuous functions that extend, that are valid for between minus infinity and plus infinity. So the more general mathematical way of representing the inner product of two functions is by using the notation brackets and comma. And in quantum mechanics, we use the Dirac notation, which is essentially the bra-ket notation. So this is basically the notation we adopt in quantum theory rather than the general mathematical notation for inner product. And we're going to say that instead of having a sum, we're going to integrate over the two functions. So we're going to have our complex conjugate here. So this is going to be a function of x. We're going to multiply it by the function psi of x, because remember, now we're not adding finite points, we're actually just integrating over the whole domain of these functions with respect to x, and we're simply going to take the integral of these two quantities. So the inner product is in essence just the integral of the two functions. By taking into account that because this is a bra, we're taking the complex conjugate of that function. And this is obviously going to go from infinity to plus infinity because we want to take the full sum of these, or of these two functions. So this is how we would define the inner product of two functions, arbitrary functions in mathematics. Now, where does this all lead? Because we started off with a question about how do we extract probabilities from a simple coin system that is represented by the sum of two eigenstates, heads and tails. Well, it turns out that the inner product is the main tool that we'll be using to extract information out of any quantum system. And we will be using it in this form in later videos when we actually start using actual continuous wave functions. But for now, I want you to notice that for a coin system, which is essentially this, so this one was the eigenstate heads, and we have the probability of tails here. We can extract the information by applying a simple operation to it. And the argument we're going to use is we are going to assume that all the basis vectors here are orthonormal. And this is an inherent property of this system. If this is a valid wave function that characterizes the system, then these basis functions need to be orthonormal. Or at least they need to be orthogonal. But we say orthonormal in the sense that they have to have unit length. So for example, this one could be represented as the column vector 1, 0, and this one could be represented as this vector. So this satisfies the orthonormality property. So now we're going to go back. I'm going to get rid of this. So what am orthonormality, right? Accidentally erased that. Okay, so we have our eigenfunction for the coin here. And what I want to do now is I'm going to extract information about the heads. So what I'm going to do is I'm going to take the bra of heads and I'm going to multiply by the coin eigenfunction. Now, we can do this in a very rigorous way by simply expanding this out. So if I take the ket of this is going to be a row vector. So this is going to be just heads. So it is going to have its scalar quantity attached to it. So this is the representation of that vector. And now we're going to have this is actually going to have another element here. It's just going to be 0, because remember that heads as an eigenstate, it has 0 proportions in tails. So this is basically a 2-dimensional vector, but it has a 0 where the eigenstate of tails is, because we know that there is no way that this coin can ever be measured in both heads and tails simultaneously. There's just no way. So the next thing is we have taken the ket, and of course we need to take into account that the probability amplitudes could very well be complex. So we're going to take the complex conjugate of them because this is a bra. Now we're going to multiply this by a ket, which is a column vector, and now we're going to take the vector of the eigenfunction. So this is going to be pH. So this is going to be pH, and it is actually not going to matter. I'm just including this here for illustration, but just to make it more general, I'm just going to use this as a simple expansion. So I'm going to write pH of H plus PT of T. So taking this as algebraic expressions, I'm just going to use the distributive law, and I'm going to say, well, this is going to be pH asterisk times pH, and now we have this quantity here, bra times H, plus 0 PT of T. And now you notice something very peculiar. This is an inner product of an eigenstate with itself. And we just said that if two eigenstates, or if two vectors are orthonormal, then their inner product should always be 1. So I'm going to write this down here. If two vectors are orthonormal, their inner product should always be 1. Or actually, the dot product with itself should be 1. And the dot product of two vectors that are orthonormal should always be 0. So something like phi and psi should be 0. So this is the correct definition. This is going to be 1 because this represents the probability, and the function is normalized, so this should always add up to 1. But if the two functions are orthonormal and we take an inner product, we should get 0. Because essentially the dot product of two vectors that are perpendicular to each other is 0. So that's the same definition we're using here. So if we're using that definition, the next thing we can do is we can say, well, H and T we already declare as orthonormal, so this has to be 1, this has to be 1. We know that this is just going to be 0. So in the end, our HC, or inner product of the heads with the C, is going to be equal to pH asterisk, or pH conjugate times pH, which we know is going to be pH squared. So look at what we just did here. We went from a probability amplitude that may have been complex. We took a measurement of this system with respect to heads. So basically, let's say we landed on heads, and now we obtain a probability, a real number that represents the probability that the coin will land on the state heads. And we notice that this is a probability squared. So in essence, the actual probability should just be the normalized version of this quantity. And we will talk more about this in the next video, but hopefully now you understand a little bit more about the inner product, and you will see that where we're going with this is we're going to be using the inner product quite a lot to extract information out of a system that is described as a superposition of all the possible states of that system. and we will continue this in the next video.